We are all learning. Our community statement has its 3 bullet points. We are all learning. Everyone has something to contribute, and no one has all the answers. With that said, please, Chihoi, it's time to share your slides.
Yeah, sure.
And it's my pleasure to introduce Chihoi from University of British Columbia, who will talk about Erdős-Ko-Rado properties of pseudo-Paley graphs of square order. Please.
Okay, so thanks for the introduction. So today I will talk about Erdős-Ko-Rado properties of pseudo-Paley graphs of square order. And this can be regarded as iteration between extremal combinatorics, algebraic graph theory, number theory, and also eidetic combinatorics. So there are a lot of interesting stuff going here. And I would like to begin with some background knowledge, and I will start from the classical Erdős-Ko-Rado theorem, which I'm sure most of you are familiar with. So the setting is that we consider K uniform intersecting family of the first integers. So by a K uniform intersecting family, I mean that for each set in this system, in this family F, it would have size K, and it's a subset of the first integers. And also by intersecting, I mean that for any 2 sets in this family, they have no empty intersection. And Erdős-Ko-Rado asks, what's the largest possible size of this intersecting family F? So there are a few cases to consider. So first, if N is less or equal to 2K minus 1, then this question is not interesting because if we consider any 2K subset, then they would intersect because N is less or equal to 2K minus 1. So in this case, we can just take the family to be all K subset. And if N is at least 2K, then the question becomes interesting. And we might want to first try to see if there is some obvious choice of intersecting family. And it's not too hard to see that if every set in this family contains a common element, say 1, then this will be a valid intersecting family. And we will call this kind of intersecting family as canonical intersecting family. And this is the terminology I would use throughout the talk. And some people also call this trivial intersecting family because the intersection of all sets contains a common element. So like this kind of set are trivial intersecting. And sometimes people also call this a star because if you try to draw the picture, then they all contain the common elements. So it looks like a star. And if F is a canonical intersecting family, then it's easy to see that the size of F is given by this binomial coefficient n-1 choose k-1. Because we already fixed a common element, then we just need to pick k-1 element from the remaining n-1 element. And the question is, can we do better? So basically, we want to ask what's the maximum size of intersecting family. And Erdős-Ko-Rado in 1961 proved that if N is at least 2K, then F is at most n-1 choose k-1. In other words, this canonical intersecting family is indeed a maximum intersecting family. And if N is at least 2K plus 1, they show the stronger statement that all maximum intersecting family are canonical. And here it's important to assume that N is at least 2K plus 1, because if N is 2K, then we can take all K subset excluding 1. Then you can show that any 2 sets still intersect. And by the way, I forgot to say that feel free to stop me and ask any questions. Okay, so this is the classical Erdős-Ko-Rado theorem. And the Erdős-Ko-Rado theorem can be regarded as one of the fundamental results in extremal combinatorics. So we would like to study the analog of Erdős-Ko-Rado theorem. And it's not surprising that it has been successfully extended to many other combinatorial objects, including matchings or secondary arrays, permutations, and vector spaces. And in the next few slides, I will also talk about some analogs of Erdős-Ko-Rado theorem on other settings. And typically, Erdős-Ko-Rado type results state that the extremal configurations must be canonical. So for extremal type problem, we are asking what's the size of the extremal configuration. So that's the first part. And the second part is more important and more interesting, which is to categorize all extremal configurations. A result is of a Erdős-Ko-Rado type if we can show that all extremal configurations must be canonical. So in the setting of classical Erdős-Ko-Rado theorem, the canonical intersecting family are given by this kind of stars. And in other settings, if we can define the notion of canonical extremal configurations, then it makes sense to try to categorize this kind of extremal configurations. And usually we say an object is canonical if it's have a extremely simple structure. And it also has to be a very rigid structure. Okay, and let's talk about the graph theory formulation of Erdős-Ko-Rado theorem. So we can consider the Canessa graph K and K, whose vertices are K element subset of the first integers. And the two vertices are adjacent if A and B have empty intersection. Then we can see that intersecting family is simply independent set, because in an independent set, no two vertices are adjacent, meaning that no two vertices have empty intersection. So that means every two vertices have no empty intersection. So that's intersecting family. So the classical Erdős-Ko-Rado theorem says that the independence number of this graph is given by this binomial coefficient n-1 to k-1. Moreover, we can characterize our maximum independence set. And in the later part of the talk, we will talk about the Erdős-Ko-Rado theorem for the pseudo-Paley graph. And there we will talk about maximum cliques instead of maximum independent set. But essentially, there is no difference between cliques and the independent set, because we can always go to the complement of the graph, then a clique becomes an independent set. Okay, and then before talking about the Erdős-Ko-Rado theorem of pseudo-Paley graph, I would like to first briefly talk about the Erdős-Ko-Rado property of permutation group to give more background and more motivation of our work. I should also try to introduce some terminologies first. So given an EKR type problem, we typically identify the combinatorial object with the corresponding graph. So for example, in the classical Erdős-Ko-Rado theorem, we would consider the corresponding Canessa graph, and we will see more examples later. Then instead of talking the Erdős-Ko-Rado property of this combinatorial object, we typically talk about the Erdős-Ko-Rado property of the corresponding graph, because there's no difference between the graph and the combinatorial problem. And given a graph, we can talk about cliques and independent set. And here I would use the terminology from cliques, but again, there's no difference between cliques and independent set. So first, given such a graph, we need to describe what are the canonical cliques. And then we can talk about the following three different notions of Erdős-Ko-Rado properties. So the first one is called the EKR property, meaning that a canonical clique is maximum. In other words, the clique number is equal to the size of a canonical clique. And the second property is called the Ekr Module Property. And this is the property that the characteristic vector of each maximum clique in X is a linear combination of characteristic vectors of canonical cliques in X. In other words, if we consider a maximum clique, then its characteristic vector must be lying in the vector space spanned by the characteristic vectors of canonical cliques. And I will explain in the next few slides why this is called EKR module property instead of EKR vector space property. And the third property is the most interesting one, and it's called the strict EKR property, which says that every maximum clique must be canonical. So you can see that the strict EKR property is the strongest one among these three. This EKR module property is slightly weaker than the strict EKR. And typically the EKR property is the easiest to study. To tackle EKR type problems, there are many different approaches. And the one approach which is very popular and very powerful is the so-called algebraic approach. And Chris Gossell and Karen Ma wrote a book called Erdős-Ko-Rado theorem algebraic approaches. And if you are interested in this topic, I strongly recommend you to take a look at that book. And typically there are many algebraic tools involved in this kind of problems. And here I just list a few, like algebraic graph theory, linear algebra, representation theory, finite geometry, number theory, design theory. And as I said before, our goal is to prove or disprove the strict EKR property. The reason I listed the EKR module property is because there's a related method, which is called the module method. And the module methods refer to the strategy of proving the strict EKR property using two steps. The first step is to first show that we have the EKR module property. And then the second step is to show that the EKR module property implies the strict EKR property. So you can see that the EKR module property says that the characteristic vector of a maximum clique lies in the vector space spanned by a characteristic vector of all canonical cliques. So suppose that the structure of canonical cliques are very simple, then we might be able to actually work out the structure of the vector space spanned by all canonical cliques. And then we just need to look at this vector space to see which kind of vectors are lying in that vector space. So in this sense, it's natural to see that if we have the EKR module property, then it might be very helpful to prove our goal, that is the strict EKR property. Okay, so now I'm ready to talk about the EKR property of permutation groups. So let G be a permutation group, and suppose that G is a subgroup of the symmetric group of the n-element set. Then we can call two elements in this group intersecting if we can find some k such as gk equal to hk. Equivalently, this means that H inverse G is not a derangement because K is a fixed point. Okay, so this is the notion of intersecting. And then we can talk about intersecting family. And again, we need to define the notion of canonical intersecting family. And in this case, if you look at this definition, you can see that if we have bunch of elements which all share the image at the point K, then they would form an intersecting family. So we will say a subset of G is canonical if it consists of all elements of the group G, which sends some fixed element I to some fixed element J. And we can associate the graph, we can associate the group G with its derangement graph gamma G, where the vertices of gamma G are elements of G, and the two elements are adjacent if only H inverse G is a derangement. Then a Maxwell intersecting family of the graph of the group G is a Maxwell independent set in the corresponding derangement graph gamma G. Actually, the Ekr module property was first defined by Ma in this context, because here we have a module structure, because permutation group G would naturally act on the vector space W spanned by the characteristic vector of those canonical independent set, which makes W a G module. And in other settings, we may not have non-trivial group action, but we can always talk about the Ekr module property. Here are some recent development of the Erdős-Ko-Rado properties for transitive permutation groups. In 2016, Mars, Beaker, and Type showed that every two transitive group have the Ekr property. And then last year, Ma and Xin showed that every two transitive groups have the Ekr module property. And as an example of the module method, Hamadi and Ma showed that under some additional assumptions, the Ekr module property would immediately imply the 3 Ekr property for some two transitive groups. But we should remark that the 3 Ekr property does not hold for all permutation groups. And one counterexample is given by Ma and Rijafima Hachacha recently. And their counterexample is the general linear group GL2Q. So these are those 2x2 invertible matrices over the finite field FQ. Okay, so now I can move to the main topic of the talk, which is the Erdős-Ko-Rado property of pseudo-Paley graphs. So first, I would like to introduce Paley graphs and some generalizations of Paley graphs. So Paley graph is a graph defined over the finite field. So vertices of the Paley graph is from a finite field, and we say two vertices are adjacent if the difference is a square in that finite field. So this is an example of the Paley graph of order 13. So we can think that the element, we can think that the vertices of this graph are the element from 0 to 12 modulo 13. And the two vertices are adjacent if their difference is a square modulo 13. So for example, 0 and 1 are adjacent because 1 is a square, but 0 and 2 are not adjacent because you can check that 2 is not a quadratic residue modulo 13. And if you look at this graph, then you can see that this is very symmetric. In the sense that if you stand at any point, then the viewpoint you get is exactly the same. And in fact, Paley graph is just a special instance of the so-called Paley graph. a Kelly graph is defined over a billion group G with a connection set S, such that S is symmetric in the sense that S is equal to minus S. Then the Kelly graph, KDGS, is a graph whose vertices are elements of the group G, and two vertices are adjacent if only if their difference is an element in the connection set S. So you can see that Paley graph is just a special Paley graph with the vertices being the element in the additive group of a finite field, and the connection set is given by the squares of that field. Okay. The story of Erdős-Ko-Rado property of pseudo-Paley graph begins with this conjecture by Van Linde and Mike Williams from 1978. And this conjecture was actually from coding theory, where they considered certain vectors of minimum weight in generalized quadratic residue codes. And that conjecture is the following. If we consider A to be a subset of the finite field with Q-square elements, such that 0 and 1 is inside the set, and the set A has size Q, and also for any two elements A and B in the set A, their difference is a square. Then Welling and McWilliams conjecture that such set A must be given by the subfield FQ. So first we can check that the subfield indeed satisfy these kind of assumptions because we can see that each element in the subfield is actually a square in a larger field FQ square. And because we know that a subfield is closed under subtraction, so that means the difference between any two elements in a subfield is still an element in the subfield. So so this kind of assumption are satisfied. And what's interesting is the converse. So we need to show that the only such subset is given by the subfield. Since we have introduced Paley graph, we can reformulate this conjecture in terms of maximum clicks in Paley graph. Because you can see that here we require that the difference between any two elements in this set is a square. So that means A minus B lies in the connection set, which means that A and B are adjacent. So such a subset A is just a maximum click. It's just a click which contains 0 and 1 in the Paley graph of order Q squared. And we can see that this is a maximum click because it's easy to show that the click number of the Paley graph of order Q squared is actually given by Q. And there are many different ways to show that. And I think the easiest way is to use pigeonhole principle to show that. So it's just exercise to show that the click number is at most Q. And then because the subfield FQ forms the click, so that means the click number is at least Q. So the click number is Q. So this is a maximum click. Okay. So this is a reformulation of Van Linde-McWilliams conjecture. And next, I would like to state this conjecture in terms of the strict EKR property of Paley graph. And to do that, I need to first define the notion of canonical click. So we have seen that the subfield FQ forms the maximum click. And because this is a Paley graph, so we know that the structure of a click is preserved under translation. And also, if we multiply FQ by a square, then you can see that again, the difference between any two vertices are still a square. So that means that this subfield FQ actually generate a family of maximum click. So we would call this family of clicks coming from the subfield FQ as canonical clicks. So these clicks are basically scratch translate of the subfield FQ. And now the question is to characterize all maximum clicks. And because of this observation, we can also do the inverse operation. So namely, given a maximum click, first we can translate the click so that 0 is inside that click. And then we can multiply a non-square to it so that 1 is inside the click. So up to normalization, we just need to classify maximum click contains 0 and 1. So in this sense, the Wellin-McGradius conjecture is equivalent to the strict EKR property of Paley graph. So the strict EKR property says that all maximum click must be canonical. Okay, so the conjecture by Wellin and McGradius was first confirmed by Brockhaus in 1984 using polynomial method. And later, Brower and Fisher provided a slightly different proof, but still relied on polynomial method. And recently, my collaborator, Shamila Scully, and I also managed to give a different proof of this result. But again, we rely on polynomial method. So polynomial method are very beautiful, and the proof of this result are not very complicated in terms of polynomial method. But I guess the difficulty is that we cannot gain something by understanding this kind of proof, because this kind of polynomial method only work for Paley graph. And we would like to look for a simple proof of this result so that we can use this kind of idea to study other objects. And in particular, in the book by GOCC and Ma, they suggested that we should use the module method to give an algebraic proof of this result. So namely, we should first prove that Paley graph of square order have the EKR module property, and then somehow the EKR module property would imply the strict EKR property. Okay, and there are some generalizations of this strict EKR property of Paley graph. So recall that in Paley graph, two vertices are adjacent if their difference is a square. But you may ask what's special about squares? And it turned out that we can replace squares by this power for any d. And that's the notion of d Paley graph or generalized Paley graph. And in 1999, Siklai showed that if we assume that d divides q plus 1, then if we consider this generalized Paley graph, which is defined on the additive group of the finite field with q square element, with the connection set being the set of these powers, then this graph also have the strict EKR property. So again, we can see that the subfield FQ actually forms a clique because we have this assumption d divides q plus 1. And then we can see that up to normalization, we just need to consider maximum clique contains 0 and 1. I would like to point out that this assumption that d divides q plus 1 is crucial in the sense that if we do not have this assumption, then we can show that the click number of this is less than Q. So in other words, in this setting, we do not expect any EKR type result for this graph, and because the click number is less than Q, and there is no obvious choice of canonical clicks. Okay, so for generalized Paley graph, we also have the strict EKR property. And in 2009, Mullin conjectured that another family of graphs satisfy the strict EKR property, and this family of graphs is given by pizza graph. And I will introduce the definition in the next slide. But I would like to point out that pizza graphs are very similar to Paley graph in many aspects, but little is known about their the structure of their clicks. So the definition of pizza graph is given by Pizza, of course. So again, it's a Paley graph defined on the additive group of a finite field with Q element. But now the connection set is given by the set of G to the power J, where J is congruent to 0 and 1 modulo 4. And here G is a primitive root of the field FQ. So you can see that if we take J to be congruent to 0 and 2 modulo 4, then we just get the set of squares. So in the setting of Paley graph, we are taking G to the power J, where J is congruent to 0 and 2 modulo 4. And the Pizza idea is that we consider a different connection set by picking two other closed sets. So Mullin conjectured that pizza graph also have the strict EKR property because pizza graph are very similar to Paley graph in terms of this kind of construction. In 2009, Mullin also generalized the definition of pizza graph, where she considered this power pizza graph. This is a Paley graph defined on FQ path, with the connection set being G to the power J, where J is congruent to 0, 1, up to D over 2 minus 1 modulo D. And again, G is a primitive root. So you can see that if we take D to be 2, then we are just taking those G to the power J, where J is congruent to 0 modulo 2. So this is just a set of squares. So we recover Paley graph. And if we take D to be 4, then we are just taking those elements G to the power J, where J is congruent to 0 and 1 modulo 4, and we recover pizza graph. So generalized pizza, a natural generalization of Paley graph and pizza graph. So we can also ask whether this kind of graph have the strict EKR property. So we consider this power pizza graph of order Q squared, such that D divides Q plus 1. So this assumption is similar to the assumption given here, because we want the subfield FQ to form a clique so that we can define the canonical cliques. So canonical cliques are just those cliques which are affine images of the subfield FQ. Okay, so we have introduced these 4 family of graph: Paley graph, generalized Paley graph, pizza graph, and generalized pizza graph. And we want to study the strict EKR property of these 4 family of graphs. And our observation is that we can treat them uniformly. The observation is that in these 4 family of graphs, their connection set are very special. And if you look at Paley graph and Giant's Paley graph, their connection set is the set of these powers. In other words, in their connection set is a subgroup of the multiplicative group of the finite field. If you look at pizza graph and Giant's pizza graph, their connection set is just a union of coset of the subgroup. And if we further assume that D divides Q plus 1, then we can further decompose a subgroup into coset of the of FQ star, which is again a subgroup. So based on this observation, we introduce a larger family of graph, which we call pizza type graph, because this kind of construction is really similar to the construction by pizza. So again, this is a Kelly graph defined over the additive group of a finite field with Q square element. And the connection set S is just a union of coset of FQ star in FQ square star, such that the connection set contains FQ star. And we will call such Kelly graph a pizza type graph of type MQ. So M is the number of coset, and Q is the, so this is Kelly graph defined over FQ square. So we have a parameter Q here. And because FQ star contains in the connection set S, so you can see that FQ forms a clique. So a subfield forms a clique. And then we can consider those cliques obtained by affine images of the subfield FQ, so that we can define those cliques as canonical cliques. And once we have the notion of canonical cliques, we can ask whether this kind of graph have the EKR property, the EKR module property, and lastly, but most importantly, the 3 EKR property. Okay, and first, it's not too difficult to show that this kind of graph has the EKR property. And in fact, we can show a stronger statement that the chromatic number and the clique number are both equal to Q. Secondly, we can show that this family of graphs are strongly regular. And in fact, this family of graph is a special case of a more general construction of a cyclotomic strongly regular graph. So I forgot to mention cyclotomic classes in the abstract. So a cyclotomic class is simply a coset of a subgroup. So cyclotomic classes is the same as a coset. And Brower, Wilson, and Sean in 1999 gave a general construction of cyclotomic strongly regular graph. So their construction is very similar to this. So they again consider a Kelly graph defined over the additive group of certain finite field, with the connection set being the union of coset of a fixed subgroup of the finite field. So this construction of pizza type graph is just a special construction of the cyclotomic strongly regular graph given by them.
I have a question. In the second theorem, you have these parameters. Can you explain them a little bit?
Sure. Okay, so the first parameter is the number of vertices of the graph. And this graph is regular because it's a Kelly graph. And the second parameter is the degree of each vertex. And the third parameter is the number of common neighbors for any 2 adjacent vertices. So for any 2 adjacent vertices, if we look at the size of their common neighbor, it's a constant. And the last parameter is the same parameter for 2 non-adjacent vertices.
Okay, thank you.
Yeah, so this is a stronger notion of regular graph, and we call this a strongly regular graph. And in particular, if we take M to be Q plus 1 over 2, we get a pseudo-Paley graph. And by a pseudo-Paley graph, I mean a graph which have the same spectrum as a Paley graph. So we know that a Paley graph is strongly regular with certain kind of parameters. And if we consider a pizza type graph of type Q plus 1 over 2Q, then we can show that it has the same parameters. And for a strongly regular graph, its spectrum is uniquely determined by the parameters, by these 4 parameters. So this means that a pizza type graph of this type is actually a pseudo-Paley graph. And then because this is in this case it's a pseudo-Paley graph, so we naturally expect that the street EKR property would extend.
We had another question in the chat from Joseph. He was wondering if these PSAR type graphs are perfect.
So I'm not sure. So I think this is called maybe one perfect graph. So if the chromatic number is equal to the clique number, then I guess it's called a one perfect number, one perfect graph. But for perfect graph, I guess we need more conditions. So the short answer is I don't know. And in fact, this result is just proved by us. So you can try to see if it's actually a perfect graph.
Okay, thank you.
Okay, and our next main result is that pizza type graph have the Ekr module property. So in particular, this solves the problem asked by GOCC and Ma. Because they want to use the module method to show the street EKR property of Paley graph. And here we show that all pizza type graph have the EKR module property. Okay. And next I would like to briefly talk about the proof of this result. So the proof is based on the observation that pizza type graph have some connection with orthogonal arrays from design theory. But first I need to introduce what's orthogonal array, what are the canonical cliques, and what are the EKR properties of orthogonal arrays. So an orthogonal array OAMN is an m times n squared array with entry from an n element set T, such that if we take any 2 rows of this array, then they would consist of all n squared possible pairs. So in other words, if we take any 2 rows, then their columns are pairwisely distinct. And because the entries are from an n element set, so the number of pairs are given by n squared. So because all columns are distinct, then it would consist of all n squared possible pairs. Okay, and there's a natural notion of intersecting in this case. So we say 2 columns. So I should say 2 columns. We say 2 columns intersect if there is a row in which they have the same entry. So they intersect in the sense that they have a common entry in a common row. Then based on this notion of intersecting, we can try to ask what are the largest intersecting family in orthogonal array. And similar to the previous example, we first associate this with a graph. And in this case, we associate this with the broad graph. And the vertices of the broad graph is just those columns. And we say 2 columns are adjacent if they intersect. Okay. Also very similar to the previous cases, we can try to define what's canonical cliques. So in that case, we will say a clique is canonical if they have a fixed entry in a fixed row. So it's very similar to the definition of canonical intersecting family in the setting of permutation groups. And once we have the notion of canonical cliques, we can talk about the EKR properties of orthogonal arrays. So it turns out that orthogonal array always have the EKR property and the EKR module property. So if we can show that we can find a one-to-one correspondence between pizza type graph and the broad graph of orthogonal array, then we immediately have the EKR module property of pizza type graph. Okay, so we just need to show this explicit connection between pizza type graph and orthogonal array. So our main result is that each pizza type graph of type MQ can be realized as the broad graph of an orthogonal array OA-MQ. So you can see that the parameter here match perfectly. And moreover, we can also show that there's a one-to-one correspondence between canonical cliques in the broad graph and canonical cliques in a given pizza type graph. So in other words, there's no difference by considering canonical cliques in either graphs. Okay, so the basic idea of this result is that we first embed a clique in a pizza type graph. So recall that this is a subset of the field FQ square into the affine plane AG to Q. So the affine plane AG to Q is just FQ times FQ. So we know that FQ times FQ is isomorphic to the field with Q square elements. So we can just find the basis so that we can embed a subset of FQ square into the affine plane AG to Q. And recall that in the pizza type graph, our connection set can be nicely decomposed as the union of coset of FQ star. And we can show that each coset in the connection set actually corresponds to a direction or a slope in the affine plane. So basically, a subset can be embedded to the affine plane if the direction set determined by this subset after the embedding is given by the direction set corresponding to the coset in the connection set. So in other words, given a subset in the affine plane, we can try to see whether this comes from the embedding of a clique in the pizza type graph by checking the direction set determined by this point set. And we can show that each direction actually corresponds to a row in the orthogonal array coming from the point line incidence. So in the affine plane, we have like Q square points, and we have Q plus one different directions, namely all element in FQ and also the vertical direction. Or if you view this projectively, then we have Q plus one element in the projective space. So based on the point line instance, so basically we have a point in the line, and if a point lies in that line, then we have the point line instance. So based on the point line instance, we can construct an orthogonal array. And it turned out that a row in the orthogonal array corresponds to a direction. So this established the first statement. And for the second statement, we can see that each canonical clique in the pizza type graph after the embedding, it can be treated as a line. So for example, for the canonical click FQ, which is the subfield, after the embedding, it just becomes a line. So a line just have one direction, right? So it corresponds to a row in the it corresponds to a row with a fixed entry. So that's a canonical click in the bar graph of the orthogonal array. Okay, and do I still have a few minutes, or should I stop now?
So if you want more time for questions at this, it would be a good time to stop now. But if you have one more message that you want to give us, then maybe.
Okay, sure. So I would like to quickly point out our result on street EKR property. So result will be very technical. So basically, we can show that for a pizza type graph of type MQ, where M is most Q plus 1 over 2, and if we have some additional assumption on the connection set, then we can show that such pizza type graph have the street EKR property. And the proof is based on the finite geometry aspect that I just mentioned, and also some result from Cater sums. And in particular, we can use this result to show that if our Q is sufficiently large, then pizza graph and generalized pizza graph have the street EKR property. But we have some counterexamples showing that for certain pizza type graph, they do not have the street EKR property. So the open question is first, try to characterize all pizza type graph with the street EKR property. And the second open problem is that we have mentioned many results and many development on EKR type result on permutation group. And we are wondering whether we can borrow those results to study the EKR properties of pizza type graph. So that concludes my talk, and thank you very much for your attention.
Let's thank the speaker. Are there questions? So I kind of, you're talking about square order. What's beyond square order? Can we also take third powers, fourth powers, or power?
So square order in particular include the case of fourth power, because if you have q squared, say if you have q to the power 4, you can just take q squared to the square. But this type of result cannot hold for example, graph with prime order. So in that case, the difficulty is really to define what's canonical click. So you can see that here we require the field structure. So we have a subfield to be a canonical click. So if we have a graph which is defined over the additive group of a field with prime order, then in that case we do not have an obvious choice of canonical clicks. So we don't know how to define the right notion of Erdős-Ko-Rado type property.
Thank you.
And actually, in the case that the graph has prime order, it has many connections with analytic numbers, in particular Riemann hypothesis. So I guess people are also very interested in Paley graph with prime order.
Oh, cool. Are there more questions?
I guess I kind of want to circle back around to what Joseph was asking about earlier. So you have a result about, chromatic number equals clique number. Mm-hmm. And you haven't followed up on whether or not that these graphs are perfect, but do you have a sense on whether or not these techniques could be extended to that?
So actually, this result can be proved by using this explicit connection between pizza type graph and orthogonal array. And for orthogonal array, we know exactly what are the chromatic number and what are the clique number. And this result just follows from that. So if we can see that for certain orthogonal array, the corresponding block graph are perfect, then we can also show that if we consider the corresponding pizza type graph, that is also perfect. But I'm not sure whether there's a classification of perfect graph for block graph of orthogonal arrays. But I'm sure there are some related results.
Okay, thank you.
Does it look like the graphs are chordal?
Say the graph are
Chordal. In other words, does every cycle have can be like connected? Like non-adjacent vertices on a cycle, can they be like, does there always have to exist such a pair?
I'm not sure. I'm not familiar with the terminology you mentioned.
Okay, because that would also prove it.
Was the graph that you displayed on the slide? So I'm trying to remember. Are these? Is the graph you showed earlier on the slides the one that was the Paley graph of 13? Is a Paley graph pizza type? I don't recall, because something was a generalization of the Paley graph.
Yeah, so pizza type graph is a generalization of Paley graph. So for Paley graph, you just take the connection set to be the set of squares, and then we can decompose the set of squares into a coset of FQ star.
Okay, could you go back to the Paley graph then that you showed in your talk? Okay. Eyeballing this doesn't look chordal to me, like 3, 12, 9, 6.
So this is the Paley graph of prime order.
Yeah.
So so we are actually working on Paley graph of 3 order, and
got it. Okay.
Yeah, they might have very different structure.
Fair. Okay.
The Paley graph of order 5 is just a cycle, right?
Yeah, it's just a cycle.
So that's not perfect.
Yeah, but again, that's
Yeah. So I'm just saying
prime
that
order.
for prime order, it's not.
Yeah. For prime order, this kind of result failed completely. We cannot talk about canonical quicksand.
Okay. Are there further questions? Then if not, let's thank our speaker again.
Yeah, thanks for listening.